In theorem 1.5.3, we show that the hypotenuse of a right triangle is its longest side. And we have to do so because we haven't yet established the Pythagorean theorem without using the Pythagorean theorem, which would make this a very quick exercise. But since we haven't proven it yet, we can't use it. So how can we show the hypotenuse of a right triangle is its longest side? Well, in the first part of the proof, we remind ourselves what the definition of a hypotenuse even is in the first place, because we're not going to get anywhere without knowing that. The hypotenuse, by definition, is that side of a right triangle which is opposite its right angle. So in the triangle ABC that's sketched right here, the hypotenuse is the side AB. Okay, so the key elements in this proof are twofold. First of all, we need some way of translating an understanding about the having a right triangle into an understanding of how its other two angles, besides its right angle, compare. So how do its other angle measures compare to that right angle? And then if we can establish that comparison, we then need to translate a fact about the comparison between angles in a triangle into a fact about comparison of side lengths in a triangle. So we need a tool that can let us translate bigger angles into bigger sides. So the first thing we need is to know how the angles at A and B compare with the right angle at C. And the tool here is that theorem 1.3.3, which constrains the total measure of the interior angles in a triangle to 180 degrees. So because A plus B plus C has to add up to 180, and because by assumption C is a right angle, making its measure 90 degrees, the algebra over on the right-hand side here justifies why A plus B together have to add up to 90. So A and B are what we call complementary angles. So the measures of angles A and B have to add up to 90 degrees. But what else do we know about A and B? We also know that the measures of angles A and B have to be greater than 0. And the reason we know that is because if not, if the measures of those angles were 0, if either were 0, then we would end up with a side which has a length of 0 opposite that angle, and so A, B, and C would be collinear. A, B, and C would all lie on a common line, and 3 points which lie on a common line do not determine a triangle. So A and B are positive angles, and two positive numbers which add up to 90 must both be strictly less than 90 degrees. So theorem 1.3.3 guarantees for us that in a right triangle, the other two angles that are not 90 degrees must each be less than 90 degrees. So what that means is that the right angle in a right triangle is the biggest angle. It's the angle with the largest measure. Now that we know it's the biggest angle, we need to translate angles to sides. How do we know that the hypotenuse, which is opposite the biggest angle now, also has the largest side length? That's given to us by 1.2.9, the angle side inequality. Remember, the angle side inequality says that opposite a bigger angle, we will always find a bigger side. And therefore, in this triangle, the biggest side will be opposite the biggest angle, and that biggest angle is the right angle at C, according to the work that we did preceding. Therefore, the hypotenuse opposite C is the longest side in this right triangle. Note that the Pythagorean theorem would have made this a very quick proof indeed, but we don't have the Pythagorean theorem at our disposal. All we needed was theorem 1.3.3 about the total measure of the angles in a triangle, combined with the angle side inequality to translate knowledge of bigger angles into knowledge of bigger opposite sides.